So, what I'm going to talk about here is the cryosphere. So there are many different components of the cryosphere. We have, I don't know if you can read this at the,
Yes, yes.
So what we have is, when you hear of the ice is melting or the ice is advancing or any of this, if you're talking of little ice age or if you're looking at in the Arctic sea ice recently, you have to split it up into the different components. You have the sea ice, you have the ice caps on glaciers, you have ice sheets, water on the planet. And so if we move to the next slide, there's you can divide it up into the glaciers, sea ice, ice sheets, permafrost, ice shelves, and snow cover. This is a map showing the average locations of where the different components are. So you can see the light green is where there is seasonal snow cover. So you can see that Europe and North America have a lot of that has seasonal snow cover. The dark green is what's called permafrost, where the ground is permanently below 0 degrees Celsius or 32 Fahrenheit. The pink bits are glaciers, mountain glaciers, which are permanent ice sheets, but on typically on mountains. The ice sheets of there's one in Greenland and Antarctica, which are almost continental, or they cover an entire island in the case of Greenland, or a continent in the case of Antarctica. So, if you move on to the next slide. Most of you familiar with the UN IPCC? Yeah, so it's the Intergovernmental Panel on Climate Change, and so a lot of people rely upon this for in the scientific community for their understanding of what's happening in the climate. So what we're finding is that when the trends of the imply that the ice is melting dramatically, the IPCC is very good at reporting that quite accurately. But we should be looking at all of the evidence for and against if you were to be scientifically rigorous. So in this short presentation, I'm going to look at what we do know about the cryosphere, not just the one.
Yeah, no.
Yeah.
Good.
Yeah. So next slide. This is based on 3 papers that we have published in the peer-reviewed literature. The first one that I'm going to talk about is on sea ice. So we published that in 2017 in Hydrological Sciences Journal, and it's a reconstruction of Arctic sea ice back as far as we could go, which is 1901, which has already been mentioned. You should go back as far as you could go. The second one is a paper on snow cover, which we just published was it April, or March or April, in Geosciences. And the third one is the one that Willie was referring to earlier on the Earth's on looking at re-evaluating the role of solar variability on Northern Hemisphere temperature trends, and that's relevant just peripherally because in it we discuss glaciers and also Arctic temperature trends. So these are the topics that we're going to do. So we're just going to look at Arctic sea ice, so this one here, and we're looking at the Northern Hemisphere sea ice. So you can see that's the grey bit up on the top. Okay, next slide. So the sea ice, you have the Arctic and the Antarctic. Antarctic is in the Southern Hemisphere, Arctic in the Northern Hemisphere. And every year, in the summer, for each hemisphere, in the summer the sea ice retreats, and in the winter it advances again. So, and this occurs for both hemispheres. Obviously the seasons are reversed in the hemisphere. But if we go on to the next slide, this is what's happened. So the Arctic sea ice area has declined since satellite records began. There's a couple of problems with that when you look in the details. First of all, it's less than, the rate at which they've declined is less than half of what the climate models were predicting should have occurred. So these are The bottom graph is what's called hindcast. So the computer models, they go back in time and they say, if we go in towards present day, what would we expect to have occurred for the Arctic? And this is what they find should have occurred. It should have been a decline of 53,000 kilometers squared per year. The actual linear trend was minus 23,000 kilometers per square year. But also, if you look, it's a lot more up and down than the model predictions should have been. And that's just one point, but the other point is that the records only began in 1978. And coincidentally, that happened to mark the end of about 30 years of Arctic cooling. So we need to look at it in the context of longer periods, as one of the questions was earlier. And here's an inconvenient truth. The Antarctic sea ice, the long-term trend has actually been a general increase of plus 10,000 kilometers squared per year. This is up till now. There's a little drop in the last couple of years, but the long-term trend has been upward. And again, the hindcasts have said that it should have been declining at minus 25,000 kilometers squared per year. So, okay, so that's an inconvenient result. We'll move, so let's ignore it for the rest of this talk. The Arctic, what happened in the pre-satellite era? There are some measurements that have been made from explorers going out on ships, from aerial reconnaissance, and from different measurements in icebreaker ships and different things like that. The IPCC decided, they used a particular data set constructed from this, which is the Walsh and Chapman data set. So the Walsh and Chapman data set, you see the red bit on the far right, that's the satellite estimate that we had. And they stitched onto it this blue, almost flat line going all the way back to 1870. And they, if you were comparing apples to apples, then you would say, wow, this is a really incredibly dramatic decline post-1970. And that's what the IPCC implied. But let's look at the Walsh and Chapman if we look onto the next slide. There is a problem with the Walsh and Chapman. And we discuss it in more details in the paper, the Hydrological Sciences Journal paper. But this is just one of the key points. To estimate the past pre-satellite era, one of their main data sets were these maps that were done by the Danish Meteorological Institute. They were issued every month. They would issue this map of their supposed sea ice extent. And so the bits that are in white are supposed sea ice. The bits in red are derived from actual observations. See these bits here? Most of the area didn't have any actual observations, so they were just guessing. And in particular, if you notice, 1952 was at the height of the Cold War. So the Europeans and the Americans were not getting, the Danish were not getting access to the Russian data. So they just had to guess what was happening. And so if you were at the Danish Meteorological Institute, you said, well, what do we tell our seafarers going out there? We'll say, there's probably ice, don't assume it's ice-free, because there might be ice. But simultaneously, the Russian meteorological agencies, they were actually monitoring the ice. So about 10, 15 years ago, I think it was 2007, there was a major digitization of all of the Russian data and a sharing between the US and Russia. And the map on the right-hand side is showing what the Russians were observing for the same month as this one that the Danish map was. And you can, I don't know if you can see it, they're kind of roughly orientated the right thing, but all of these blue patches there, where it's supposed to be ice, it just said there could be ice there. So if we move on to the next. So we went and we looked and said, well, you can't just do that. You can't assume apples, treat apples and oranges as being the same, other than they're both spherical and both fruit. But you need to actually try and calibrate the different data sources so that they are giving similar behaviour. So that's what we did. For brevity, because I know we're stretching on, the details are in the paper, but basically we took all of the publicly available archived estimates of sea ice, and then we compared them using Arctic temperature records, and we tried to see if there was a consistency between the temperature trends and the observed sea ice, and we adjusted, we calibrated the different sources accordingly. This is what we find. This is for the summer, and you can see the CMIP5. This is the sea ice modelled hindcast for sea ice is the top chart, and you can see they were predicting almost nothing, and then a gradually accelerating decline in sea ice in the Arctic. The bottom is our best estimate of what's actually happened. Now you can see there's large error bars, and hopefully with future work we can try and get more information and improve it. But you can see you have this multi-decadal, the Arctic was expanding in the early 20th century, then declining, and then expanding, and then declining. And it's not quite as dramatic. It doesn't seem to match well with what the models were predicting should have happened. And just to look up close, yeah, you can see periods of growth, melt, and melt. And technically, and it's a shame that one of the people that wanted to know about this is why I was saying, talking about unprecedented or the hottest or whatever. Technically, if you ignore the error bars, you could say that from 2005 on, it seems to be that colder. The mean is lower than the earlier one in the 1943. But unfortunately, there's error bars associated with it. So you can see that the upper and lower error bars, there all remains within the observed range. So what we're saying is, first of all, next slide, the IPCC, when they're looking at snow cover, this is what they describe. They said over the last 2 decades, Northern Hemisphere spring snow cover has continued to decrease in extent, and specifically they say it declined over the 1967 to 2012 period, and that's one of the key results according to the IPCC summary for policymakers. And I want to say that we could talk about the difference between the full reports and the summary for policymakers, but this is what the summary for policymakers took out as the key result. So another point is they didn't actually mention the computer models in this particular case. Next slide. Why did they talk of this spring? Well, what about winter and fall? Well, the top graphs show the winter and fall observed snow cover trends for the entire Northern Hemisphere. And the bottom ones show what the model hindcasts expected should have occurred. I think you can see that they don't match very well. In fact, we've actually had an increase in Northern Hemisphere's snow cover in the autumn and in the fall, or in the winter. So the next slide. The other thing is, why pick 1967 to 2012? This is again what I was talking about earlier on. You shouldn't be, linear trends are not really a great thing when you have non-linear data. And you can see here that if they had, this is an estimate that was if you look at the trend from the beginning in 1920 of the data up to 1967 was actually increasing. and it's slightly increased since 2012. So what we were pointing out, and this is what Michael was mentioning earlier on, if depending on whether you depending on when you stop and start your linear trends, you can get any value you want for this. So the next slide. This is for the annual trends. So this is the average over all 4 seasons: winter, spring, summer, and fall. And you can see a slight linear trend decline. But you notice that the last 2 years are actually slightly above the 50-year average. And the climate models expected that it should have been a continuous decline from CO2 induced global warming, and that the snow should be disappearing, but it's not. I'm thinking, because this is a much longer one, that I'll finish this presentation now if we move on to the next. So any questions on the cryosphere?
Especially here in hot, arid California.
Yeah.
Are glaciers melting? Can you explain that?
So here's the problem. Glaciers, I don't know, some people have mentioned there was a little ice age. So the term little ice age was coined, made popularized by Professor Jean Grove, who passed away in 2001. She was trying to describe the widespread advances of glaciers around the world from 1600 to 1900. And so it was well documented that the glaciers were advancing for the last 300 years. Many glaciers have retreated since 1900. As you mentioned, there are some that are advancing, some that have remained static. When you average over all of them, they seem to have been retreating. But the problem is, if you look at, these are the total number of glaciers that we have glacier length records for. And you can see that the black is from the Alps. The red is, or blue is for the southern hemisphere, and the red is for the other regions, or the total of them all. So we have like a very limited amount of data, especially as we go further back. Almost no glaciers go back. Most of them start in the 1900s and in the 1960s. So we are dealing with very limited data. The few glacier records that we have that go back to the 1600s suggest that we had a period of glacial advance for several hundred years, and then around 1900 it switched to periods of glacial retreat. So we're talking of centennial scale trends. So maybe if you'd look at the next slide. Oh yeah, so you've seen this one. This was the one that Willie was showing.
Oh, that one. Yeah, this one is okay.
So just to show this is just to show another example of what Willie was saying. When we looked at this Northern Hemisphere rural composite, we compared it to whatever different data sets we could find, and one of them is the estimates of temperatures derived using these glacial length records. And you can see the yellow is for the Northern Hemisphere. You can see they're saying the temperatures increased up to 1940s, then decreased, and then increased again.
I think because of so much controversy, since the chart itself I just pointed out, that was the fight among those guys. They were saying that we were lying and all those things. They were just arguing for those tiny little portions of the data. I mean, it's just crazy like hell. I think maybe...
Yeah. Yeah. So, questions on that, on this? Yeah.
I remember reading that because of the shrinking of the northern polar ice cap, that there would be massive opening of commercial shipping lanes.
Yeah.
And I felt that, how do you get any better evidence than that? But I think it was a myopic, they just looked at a short period and then extrapolated it out.
Yeah.
So is there any shipping lanes opening that are...
No, I will say that if you actually look at, we went and studied trying to find old records, you actually can find that a multi-decadal things in the sea ice. For instance, you could go back to people like Admiral Franklin in the 1840s, who went and he reached, I think it was Prince Charles's Island in the Canadian archipelago, and then he got frozen there, and it died. The whole crew seemed to have died tragically, and then the next several years after that, nobody could get as far as he was doing. So it was a big reward to try and find the crew of Franklin, and they eventually found in a few years ago, they were able to get to the place where the second of Franklin's one. They managed to get the boat of the two ships. Only the second one they only got a few years ago. So we have these dynamics. There's another thing of there was a Russian tax collector, Semyon Desnev, I don't know if I'm pronouncing it correctly, but in the 1640s he used to go to try and get a shortcut. He was up at Siberia, and so he said, oh, it might be quicker if I go from this up above Siberia all the way around the Bering Straits and get to the other side of Russia that way. And he failed in his first year. The next year he succeeded. And if you were to look at the path that he took and compared it to the 1978 Arctic sea ice extent, he'd never have made it. I think he would have had to go up to I think we estimated it was something like probably 2005 in order for him, Semyon Desnev, to reproduce the journey he did in 1640. So we were having a lot of dynamic back and forth. Any other questions on the glaciers and cryosphere, or should we move on to the next talk? That's it.